Ever pondered upon the mysteries of the early universe, the origins of everything we see around us today? The early universe is an enigma, a vast expanse of space and time that challenges our comprehension. It's a place of extremes where the rules of physics as we know them are stretched to their limits and sometimes even broken. It's a realm where time and space were born, where matter and energy first came into existence. From the smallest subatomic particles to the largest galaxies, everything we see around us today traces its origins back to this early universe. Yet despite all our scientific advances, the early universe remains a place of mystery. Its vastness is so immense, its conditions so extreme, that we struggle to fully understand it. Yet we are not without tools in our quest to unravel these mysteries. Enter the world of theoretical models, a realm where cosmologists weave intricate tapestries of mathematics and physics to explain the universe's infancy. These models are our best attempt to reconstruct the history of the cosmos, to provide possible explanations for how the universe evolved from its initial state to the reality we observe today. From quantum field simulators that recreate different versions of curved spacetime, to simulations of vacuum bubbles that might create and destroy universes, these models offer fascinating insights into the early universe's dynamics. They allow us to ask daring questions, to probe mechanisms that govern spacetime, and to explore uncharted territories of quantum physics. Diving into the theoretical models of the early universe, we embark on a journey back in time, to the very beginning of everything. This journey will be full of surprises and discoveries as we delve into the complex and captivating world of cosmology. So buckle up and get ready for an adventure across space and time as we explore the enigma of the early universe. Theoretical models, the tools of cosmologists, serve as the blueprints of the early universe. These models are not mere flights of fancy, but rather intricate constructs of mathematical equations and physical laws. They're like architect's plans, detailing the structure and mechanics of a universe yet to be. At the heart of these models are the laws of physics, those fundamental rules that govern the workings of our universe. Just as an architect uses the laws of physics to ensure a building doesn't collapse, cosmologists use these laws to predict the state of the early universe. These laws encompass everything from gravity, the force that holds planets in orbit, to quantum mechanics, the theory that describes the behavior of particles on the smallest scales. Creating a theoretical model is akin to solving a complex puzzle, where each piece represents a different physical law or mathematical equation. The goal is to assemble these pieces in a way that accurately reflects the early universe. This is no easy task, as the early universe was a place of extreme conditions, far removed from our present-day experience. Once a theoretical model has been constructed, it's not simply filed away. Instead, it is rigorously tested against observational data. This data comes from a variety of sources, including telescopes that peer deep into the cosmos, revealing galaxies from billions of years ago. If a model's predictions align with this data, it's a strong indication that the model is on the right track. However, if the data and predictions don't match, it's back to the drawing board. Through these models, cosmologists attempt to paint a picture of the early universe, one mathematical equation at a time. It's a challenging endeavor, but one that brings us closer to understanding our cosmic origins and the nature of the universe itself. Now, you might wonder, what do these models look like in action? Well, imagine a team of physicists using ultra-cold atoms to simulate different versions of curved spacetime that correspond to models of the universe. This isn't a scene from a science fiction movie, but a real experiment conducted recently. The researchers cooled potassium-39 atoms to temperatures just above absolute zero to form a Bose-Einstein condensate, which was shaped like a two-dimensional pancake. By running sound waves through this condensate, the team was able to examine the physics of each model and validate the simulator approach. This experiment didn't confirm or refute any particular models of the early universe, but it provided a benchmark for the simulator's functionality and opened up possibilities for further exploration in quantum physics. Now, let's take a leap into the concept of vacuum bubbles. This is another intriguing theoretical model that scientists are studying. These bubbles, manifestations of false vacuum decay in quantum field theory, can potentially create and destroy universes. A recent simulation included variables that previous models omitted, revealing an interesting possibility. These bubbles might form in clusters rather than randomly. This finding could help scientists identify observational signatures of these bubbles, and could also suggest that our universe may have been born as a true vacuum bubble within a multiverse. Lastly, let's take a trip on a cosmic time machine. Scientists have developed a technique to fast-forward simulations of the cosmic web, a network of large-scale structures in the universe, to its present state. This allows them to study the evolution of observed cosmic structures over billions of years. The outcome? Simulations that merge with observations from the Hubble Space Telescope's Cosmological Evolution Survey to study early structure formation and match galaxy properties. This technique can shed light on the nature of dark matter and provide insights into the morphologies and merger rates of galaxies in high-density environments in the early universe. These theoretical models, though complex, are our best shot at understanding the early universe and its many mysteries. These theoretical models are not just academic exercises, they have profound implications for our understanding of the universe. And it's not just about understanding the origins and evolution of our universe, but also about deciphering the enigma of its present state and what lies in its future. Consider the implications these models have on our knowledge of dark matter. This elusive substance has been a cosmic conundrum for decades, influencing the universe's structure and expansion, but remaining invisible and undetectable. Theoretical models allow us to simulate conditions of the early universe and observe dark matter's hypothetical behavior, bringing us a step closer to uncovering its true nature. Then we have the formation of galaxies, grand cosmic structures composed of billions of stars, gas, dust, and dark matter. Each galaxy is a universe in its own right, with its unique history and evolution. Theoretical models of the early universe provide us with a cosmic time machine, enabling us to rewind the clock and observe these galaxies as they emerge from the primordial cosmic soup. This offers invaluable insights into how the galaxies we see today came to be. Moreover, the evolution of large-scale structures in the universe is also a key area where these models leave their mark. The universe isn't just a random sprinkling of galaxies, it's a complex network of galaxy clusters and cosmic strings, often referred to as the cosmic web. Theoretical models help us understand how this web came into existence, how it evolved over billions of years, and how it might change in the distant future. But the impact of these models isn't confined to the realm of cosmology. They also have far-reaching implications for fundamental physics, challenging and refining our understanding of quantum mechanics, general relativity, and perhaps even unifying them into a theory of quantum gravity. Theoretical models of the early universe, hence, are not just about the past, but also about our present and future. They are the lenses through which we view the cosmos, shaping our understanding and guiding our quest for knowledge in this vast, mysterious universe. The journey to unravel the mysteries of the early universe is far from over. Indeed, it's a voyage that's just hitting its stride. Theoretical cosmology is a field marked by relentless curiosity and the insatiable desire to understand the fundamental workings of our universe. It's an arena where audacious ideas are welcomed, and the only limit is the boundary of our imagination. The challenges we face are immense, from simulating quantum fields with ultra-cold atoms to search for clusters of space-time eating bubbles. The tasks at hand are nothing short of Herculean. But these obstacles don't deter us, rather, they fuel our pursuit of knowledge. Theoretical models are our guiding light in this quest. They offer us a framework to test our hypotheses and make sense of the cosmic phenomena we observe. They're the blueprints we use to construct our understanding of the universe, one discovery at a time. And the possibilities that lie ahead are as vast as the universe itself. We're on the brink of uncharted territories, venturing into realms of quantum physics previously untouched. We're probing the fabric of space-time, the nature of dark matter, and the origins of cosmic structures. Each day brings us closer to new revelations. As we continue to refine and develop these models, who knows what secrets of the universe we might uncover next. The early universe, a topic as vast as the cosmos itself. We've delved into the enigma and explored theoretical models, but the journey doesn't end here. This is an open forum for cosmic curiosity. Do you have questions? Have some thoughts to share or theories to propose? The comments section is your space to engage, to question, to wonder. Your input is the fuel that propels this exploration forward. Don't forget to like, comment, and share this video. Let's continue to explore the universe together, one theoretical model at a time.